right, we might as well get going. I'm sure some other people will sneak in on this crazy wet day. I don't think it stopped raining at all. Alan disagrees, but you know, at least as far as I could tell, it's just a downpour all day. It's what? At some point in time. At some point in time, somewhere on the earth it didn't rain, probably. All right, so here's what we're going to talk about today. First things first, very good job on the sorting algorithms. We're going to grade those. Hopefully you've either gotten an email or you will get an email from a TA or me over the next day or so that says when to sign up for in-person grading. I think you'll like the in-person grading. It's not supposed to be anything stressful, and I don't think it will be. But you're basically, you go in and you sit down with a couple of TAs and you talk about your code. You talk about the results for these tests that we ran, and we ran like 1,000 tests on your code and timed everything. You're going to talk about that. You're going to talk about how it performed. If you happen to have any errors, like things failed, maybe you can figure out why they failed. A lot of people, for whatever reason, well, I know what the reason is. You didn't test your code, but didn't test the code on interesting sorts like one number. Let's say I pipe in one number. Does your program sort it correctly? It should just put out one number. Or 0 numbers. If you have a blank file, it should spit out nothing. Right? Some people segfaulted on 0, right? Which is too bad because it was probably a one-liner. But you can talk about that in your little grading session, right? So it's not like a blind, oh, it failed, click the button, right? You can say, oh, look what happened. I did that. You can look through the code. Anyway, you have about 20 minutes to do it. And it's, I think it'll be all right. Any questions on that? On the grading? Homework 5? Yes? Grading's going to start this week. Hopefully it'll get done. But I'd like to get everything done by Thanksgiving. But because this is a crazy time of year, it may slip a little. But you should, if you don't get an email from your TA within like a couple days, just email, put something on Piazza or something, and I'll check it. All right. Anything else? OK. So today we're going to talk about, we're going to continue with graphs. But probably, in some sense, more importantly, we're going to start you off on the SongSearch project. It's the last project of this semester. And it's a hard one. We've given it before in previous years. People end up generally liking it in the end. They think it's an interesting problem. But it's just one of those things where it's like a lot of work, and your head kind of explodes for a little while you're trying to figure it out. So that being said, I will say it again like I say it every time. Start it now. Just work on it a little bit for every day. You will be required to have a design document, which I'll talk about as well. OK? So we'll get into that. We're going to talk about SongSearch. I'm going to show you a little demo of it, of what I expect. And we'll talk about the Unix tip of the day, which happens to be related to the SongSearch. I'll show you why. And then we'll get into more stuff on graphs. We're going to practice, like you guys will actually practice doing Dijkstra's algorithm on paper for a little bit. And then we'll talk about some other algorithms. OK? Anybody have any other questions at this point? All right. So the final assignment. You guys have gone, obviously you guys go to Google all the time, right? And you go to Google and you do a search, and you search through basically the entire internet as far as we're concerned for Google. And the search results come back pretty quickly, right? Did you guys ever look at how quickly search results come back from Google? Like if you go to Google and you type in a search like, what do you want me to search for? Chimpanzees. First of all, Google's good enough to like start you out by doing that, by like chimpanzees. Hang on. Chimpanzees. So it took, according to this, 0.25 seconds to do that search. So basically, Google's able to search the entire internet in 0.25 seconds. Now, what does that mean? Well, are they really like, OK, guys, somebody in the background's like, OK, guys, here's the internet. Where's chimpanzee found, right? It's not quite that subtle. Right? With Google, what they do is actually, this is actually really cool. As you send your search to Google, they'd actually send your search term to about 600 or 700 different computers. And it all fans out. And all those computers have like a part of the internet in their database. And the first one that gets a hit, it basically returns to this main server that compiles them all and then sends you back the results. And it can do it really, really fast. Right? So what that means is that Google is not sitting in the background going, oh boy, here's the internet. Where do I find the pieces? Right? It's already done the database. It updates it every day. but it does, like in the background, before you ever make a search, it's figured out the data structures and put everything in there so that it can do it really fast. Max, you had a question?
Does the 0.25 seconds include like network latency?
As far as I know, the 0.25 seconds is everything, but it may not include network latency. But I think it is. I think it's basically from the time you hit to when it comes back is 0.25 seconds, at least to your browser or whatever. Or at least it must not be to your browser. It must be when it leaves the search page. That's what it is, or when it leaves their back end computers, right? Yeah, Federico.
I just tried it on my computer and it's 0.396.
Yeah, well, it's 0.396 because your computer might have gone to a different set of 600 computers, right? Which is, so basically it's not perfect and it's not the same every time, but yeah, a different set of 600 computers might have been doing your search. What would be really interesting is to see if you got the exact same list of search results too, because Google's like, they're a little bit fuzzy with some of this too. They don't always give you the top 10 results that are like every single time. It also depends if you're logged into Google, because they kind of know what you like also. It's a little scary, but they will tailor your results to your location, to previous things you've searched for, and so forth. They're really clever about it. Yeah, Dave.
I don't know if anyone else noticed this, but for me, if I type in like comp 15 in Google, like first result is class.
I think that happens all over the world because we're the only comp 15 class maybe. But yeah, you're right. If you type comp 15, it's the first hit.
I do see like
Yeah.
other, I don't know, classes.
Other classes?
That kind of pop up for other universities, but I think in general things that have to do with Tufts always come up for me.
Oh yeah, probably because of your location, really. Yeah, or it's just because Tufts is awesome. But you know, what's that? It could look through your email too. Yeah. Can it see your history? They know you. Trust me, Google knows pretty much your history. I mean, they're really good at that sort of thing. So, but the point is that there's a huge, huge database, and Google is able to return the results like lickety-split. Okay? What we're going to do is the final project, the last one, woohoo, homework 6, is basically taking a large database as far as we're concerned, a 200 megabyte long big database with 172,000 songs and lyrics in them. Okay? And those songs and lyrics are basically, I don't know where they came from, but I think they're like an open search engine sort of thing that somebody scraped off a few years ago. And there are like every song you can imagine in there. Okay? What I'm going to do right while I'm thinking about it is I'm going to show you what your program's going to do. In here, I wrote this program a few times last semester, and I'm going to run it for you right now. And what you do is you just type the SongSearch and then the name of the database file. This lyrics_full database is the huge one. And I'll show you how you can make it so this doesn't go into your directory. It's actually pretty easy. But once you do this, for testing purposes, it will start printing out the number of the song that it's gotten to 1,000 at a time. So basically, right now, it's going through and it's taking 11,000, 12,000, 13,000, right? It's got to get up to 172,000. So it's reading in the database, and this is as fast as I could make it, right? Cranking through this stuff. Those are real songs. Somebody earlier said, "Are those real?" They didn't recognize anything. But yeah, Blink 182, you know. But it's so this is only 1,000 at a time. Oh, by the way, I should say this is an open database on the internet, so there's bad words in there. But just so you know, so don't be offended if you make a search and you're like, "What does that mean? That's disgusting," or whatever. So, you know, please don't take offense at that. But anyway, it's going to crank along. So it's still got to go through 100. What did I say? 117,000, something like that. 217,000. So we'll just let this crank along for a while. Let's see. I think we will. There we go. And I'll talk a little bit more about it. So with that many songs, your database, number one, it's going to take up a huge amount of memory. We're talking like 10 gigabytes of memory probably, right? Even though it's a 200 megabyte file, you've got to put it into a form such that you can get out the data the way you want it. So it's going to take a lot of memory. Maybe not that much, but it could take up to that much. You need to use efficient data structures, right? That's like the key here. You have to find some way of storing your data so that you can get to it fast, right? If you're thinking linked list, you're probably going down the wrong path, right? Because this is not going to be fast. And I know you love linked lists, I know, but it's not going to be very fast. So what we're going to try to do is to get you thinking about this by next Monday. That's this coming Monday. You're going to have a design document, which means that you have to think about this project, read the documentation about it, which is 9 pages long, but most of it's an FAQ. I'll talk about that in a minute. Read the design document, or read the assignment document, and then lay out a plan and say, here's what I think I'm going to do. And then when you have that plan, come to office hours or see me or whatever and talk to a TA or me about it and just get it checked off. So if you said, I think I'm going to make 3 linked lists for this thing, I'll say, yeah, it's probably not a good idea. Go down this direction instead, right? So you've got to think about a lot of ideas for this. It'll take a couple days to think about that. But don't wait too long, because you're going to have to start writing the code pretty soon. Okay? Anyway, you're going to provide that through the makefile. You're just going to provide that to the server, and we'll just take a look at it. Okay? The actual code is due December 7th, which is like 3 weeks from yesterday, maybe. So we're kind of compressed on time a little bit. I mean, there's Thanksgiving in the way, and everybody's got lots of other stuff. So you're going to have to be working on this pretty steadily. Okay? All right. So let's go back and see if our thing is done. All right. Finished reading songs. Okay? I don't know what the Zulfu, Livan, and Eli title, whatever. But here's what you do. Somebody give me a search term. I'll give me one. Boston. Boston. Right? Boom. Did you see how fast that searched? It was like ding, like that, right? Because my algorithm, my data structure took a long time to get it into the right form. What's that? I'll search chimpanzee in a sec. But I want to show you what this actually prints out. This prints out a lot of stuff, right? It prints out, OK, first of all, let's see. Here we go. It prints out the title of the song, a song that matches. Then it prints the artist. We are not searching for artists or titles. If you search for a title, it should not return anything, unless the title happens to be in some other song. We're only searching one word at a time. We are not searching sentences, and we're not searching phrases, and we're not searching that. Okay? So it's much easier in that sense than you might have been considering. Okay? But it prints this out. Then it prints out what we call the context. And the context is, so there's the word we were looking for. By the way, I typed it in as lowercase. No, I didn't. I typed it in uppercase. But if I had typed it in as lowercase Boston, it still would find this one. It would also, notice there's a comma there. It would also find this, because this is technically, as far as the program that reads words in, Boston comma is one word with the comma. Okay? So with the context, here's what it does. It prints the word, and it prints 5 words before, 1, 2, 3, 4, 5, and 5 words after, 1, 2, 3, 4, 5. Okay? And that has to happen no matter how big your song is. If the word happens to be at the beginning of the song, it's not going to print things before that, but it's just going to start with however many words up to 5 before the song, before the word.
So would it only ignore punctuation? Like if you said like 2 ends by accident, would it not match that?
Right. It only ignores punctuation, so B-O-S-T-O-N-N is not in there. Let's search for B-O-S-T-O-N-N. Let's see what happens. B-O-S-T-O-N-N. Nope, nothing. OK, so there's no words in the dictionary that do that. Yeah, Danielle.
If you were to search a word that like is a smaller word.
Yeah. Well, if you search a smaller word, you only match up to the word excluding punctuation. OK, so get rid of the punctuation. So here's what you do. You get rid of the punctuation, and you make it lowercase. And I've already given you the function to do that. Like in the document, it says how to do that. And then you take that word, and any other word that would match that by also doing the same thing fits. OK, so if you search for lowercase, let's search for Massachusetts, but lowercase, right? Well, it'll find all the Massachusettses, right, with an uppercase as well, and a lowercase. OK? Yeah?
So if you said Boston, comma, it would print out Boston with
Let's see. Boston, comma. Yep, prints out all the Bostons. Because it ignores this punctuation in the search term and then ignores it there. OK? And this is kind of what Google does, right? They don't worry about punctuation a lot of times. OK? You can force it to, but that's it. It's even got VeggieTales in there. Yeah? Search for what? B-O-S-T-O? Sure. So Bosto did not find anything. OK? Yeah. Yeah?
These are alphabetical by artist.
OK, here's how it comes out. Now, when you search for Google, what do you expect the top results to be? The most relevant. So this is the same idea. Here's what we're defining as most relevant. The number of times that word appears in the song. OK? So if I do Boston, the first song that you should print out is the one where the Boston appears the most times. And I don't care about ties. If 2 songs tie, do them in any order. Or 10 songs tie, do them in any order with a number of times. OK? You only print the top 10 songs that match. but you print every lyric in all 10 songs that match. Okay? Does that make sense? Yeah.
So why is this one all the way at the bottom?
Which one?
The one visible right now.
Sorry, this one?
This song.
Oh, this song is at the bottom because somewhere up the line, this song, like other songs, had more instances of the word Boston in them. You see? This one has the least. Okay? So yeah, this is a long list, right? Wait, let me start over here. Boston. There we go. Okay. So up here, it's a pretty long list. Oh, you know what? I screwed up. I forgot. I have some other debugging stuff in here. So don't worry about all that. That's all the debugging stuff. Well, actually, the debugging will tell you something about it, actually. It's going through all this stuff. So yeah, so like some of these had one hit for Boston, like 10,000. And what it's doing is it's actually sorting this as it goes, kind of. It's keeping the top 10 list. Okay? What did I point at? Oh, no. OK, see, I told you. I told you have to be a little careful. Yeah, see, I told you. I warned you. Didn't I warn you? I warned you. Point is that the ones at the bottom are the ones of the top 10 that have the least. In other words, of the ones where there's so many instances of Boston, just the top 10 songs. So VeggieTales, this one happens to have a ton of times when it says Boston in it, but it's still the 10th.
Okay.
Right? Yeah. Yeah. And yes. What else should I search for? No bad words. Although it seems to not matter, does it? What else? Anything else? Supercalifragilisticexpialidocious. Did I get that right? I don't know. We'll find out. Look at that. There you go. Right? Let's see. Well, there's, oh, geez. I'm never searching for anything again. Yes, there was another bad word. Anyway, there are a few songs that have it in it. Yeah. So as you'll see, this database is huge. It's got a lot of stuff in it. Yeah.
I wanted to take if you search for a more common word like the.
Yeah, good question. So I have it set up so that even a common word, it'll go through a ton of songs, right? This is this is going to take forever. The way I have it printing out, it would take more time, but hopefully not too much. See, it's done, right?
A lot of the printing is causing that.
Yeah, a lot of it's the printing part. Yeah, if you didn't print it out, it'd be pretty good. But yeah, at first I thought, nah, let's not search for it. But why not? I'll let you search for those words too. Doesn't really matter. All right. Okay. So how do you end this? You actually, by the way, it should print it all out, and then it should say end of report. Okay. This is as if a computer is in the background, which could be in the background saying, what's your output going to be, right? It'll say end of the report. And then if you want to quit, because remember, I can keep searching and it doesn't reload the database. Like that would be bad too. If you search Google and they're like, hold on, we're reloading the database, right? You don't want to do that. It's all loaded and it just lets you research, right? Until you type BREAK, and notice how long it takes from when I hit break now. Well, that was pretty quick. It was actually pretty quick, but sometimes it takes time because it's got to clean up after itself. Like all the deleting of like 200 megabytes worth of, or 10 gigabytes worth of data takes a while. Yeah. It could, but we don't like to do that. Right. We don't like to do that, yeah. So anyway, I had timed this. The actual reading in of the database is about, in this case, takes about 1.5 minutes or 2 minutes. You should shoot for 3 to 4 minutes, like reading in the database. Some people do it faster, but they store less. Like you could read the database in 20 seconds, but you wouldn't have the structure to do a fast search. So there's a bit of a trade-off there, right? So you have to be a little bit careful there. Let's just, there we go. OK. What else on this? Talked about the design document. This is the output. We already talked about this. Any other questions on the output? Yeah?
Do we have to have all that stuff at the beginning where it was like hits?
No. That was just my own debugging. I'd forgotten to take that out before I showed it to you. This is all you need to put out. You do the search, and then the next line should start with title, Boston, Kenny Chesney, whatever, right? That's all you need to print out. And then you have a little, at the end, you have that end of input or end of report. OK, anybody else? OK, let's see. Yeah. I give you the code that actually reads the database word by word. In other words, it will read in and it does it by song. So basically, it'll read it in, and you'll have the song title, the artist, and a word. And then the loop will repeat, and you'll get the song title, artist, and the same and another word, until you get a new title and artist. Okay, it does that. You have to figure out the function that's going to handle that word and putting it into the database. It's tricky. The punctuation, I've already talked about that. I give you a function that will strip the punctuation out of that. But the key to the punctuation is interesting. You search for a word, you have to keep the word basically in two different places, because you need to keep the unpunctuated word and the punctuated word. Okay, so you have to think about these ideas. In your document, design, you'll think about it. And I talked about the context. Okay, any questions on that one? Okay, all right. It's not trivial to do this reading in, like the actual convert it into your database, but that's it. I give you lots of smaller data, like lots of, there's a Rick Astley database, which is really small. It's like 10 songs. And you can test on that. Instead of testing on this huge database, which takes minutes to load in, and it might crash your program, you test it on a smaller one. And then eventually, the last couple days of the project, put it in the big database and say, let's see if it works on that. Okay. Minute or two. Bad engine. If you don't do it right, it could take lots. I do know people last year who tried to use like linked lists and things, and it just would never finish. Like we never got it to finish because it took too long. We'll probably test yours and give you about 7 to 10 minutes. So if it's longer than that, you need to rethink something. Okay. All right. Yeah.
In your fast loading program, do you use only data structures that you use in this class?
I used only data structures we used in this class, and I made the hash tables myself, and I used vectors. I will talk about you can use a vector, but that's it. You're not allowed to use the hash map or the other built-in C++ things. Sorry, you have to build your own. Okay, we talked about ranking the songs, up to the top 10 songs. You can use the vector template. So a vector is just a dynamic array that's built for you. We've used the stack and the queue before. A vector is very similar. If you want to use a vector, it will save you some time in building a dynamic array. So if you do have various parts, hint, hint, you might want to keep the songs in some sort of dynamic array, then I would use a vector. Okay. Well, and Wednesday I'll talk about vectors. Like I'll show you how to use them. Okay. And then finally, we mentioned this already. We're really looking for speed at the expense of memory. This is why you might take gigabytes of memory for your programs. Okay? You have to keep all the lyrics in memory, right? But you also have to keep the structure of the alpha-only words to do the searching. You don't want to keep all the words and then try to parse them out and take out the punctuation as you go. That would take way too long, right? So you need to keep the structure that has all the, quote, alpha-only words. What that means is that the following will all match the same thing. Were, we're, a W apostrophe, E apostrophe R E, and were with a comma all match were. Okay, so you might search for were and get all the weirds, and it's weird, but that's too bad. For our database, that's too bad. Okay, so that's a lot of stuff. The document document about the project, it's 9 pages long, but most of it is an FAQ from questions people asked last time. So read that first, and you should get many of your questions answered. Okay. All right. Any other questions? I think you'll enjoy this. It's going to be hard, though. Yeah.
For the write-up thing that we need to do, it says we can talk to our TA in lab.
You can talk to your lab TA. If you're done with the lab,
Is that like
grab your TA. Oh, today or tomorrow. I know, that's true. Today or tomorrow, it's a little bit late. That's a good point. So you probably won't have a chance, unless you want to do it like right now. But I would probably wait. You'd probably go in later in the week. Okay. Yeah. And if we need to bump that a day or so, I'm not too worried about it. But I want you guys to think about it. OK? All right. Anything else? Next week, we don't even have labs, so I guess that doesn't matter. Yeah. All right. OK. So that's that. Symbolic links. This is the Unix tip of the day. That huge lyrics database, you don't want to put that into your home directory. It's like 200 megabytes, and you guys don't get that much disk space to begin with, and it'd be silly to be copying that around. So what you can do is you can type the following. Type ln, which stands for link, -s, which stands for symbolic link, which just means that it's going to be like kind of a fake link. And then you type the name of the lyrics database. That whole thing's the name. And then if you are in your home folder and you just type some other name, when you look at this file, it will be the huge database, but not really. It's like a fake. It like fakes out the disk system. But that means that you can have like a file in your folder that really is located somewhere else, and it just saves disk space. Okay? If you have trouble setting that up, let me know. But you probably won't get to that part for a week or two before you get the assignment done. OK. Questions? All right. Let's go back to Dijkstra's algorithm. I'm not sure I have enough of these to hand out. I think I do. Once you start handing those back there, you can start handing these back there. And then you start handing these back here. And I've got mine over here. Here's what I want to do. See this table up here? We're going to practice doing Dijkstra's algorithm, which we talked about last week. I will help walk people through it a little bit. But basically, what we're going to do is for each vertex that we're dealing with, we're going to fill in the details here and fill in the previous if that needs to be changed, and whether or not it's known. And then we're going to go across and do this for the crazy-looking graph up there. Okay? And if you missed the lecture the other day on Dijkstra's algorithm, you'll be a little confused. But we'll go through it, and it's all on the video if you want to see it. Okay? All right. Are we going to have enough to go around? There's a big stack. Where's the other big stack? Are there any other big stacks? People over here gotten it? Uh-oh. Let's see. One, two, three. There might not be enough. You might have to go one up. Well, there's a big stack there. We'll see. OK. Here's what I think. Take a couple minutes. Get yourself situated with this. I will put the table on the board, and then I'll start going through it. So look at it now, and we'll do that. Did you guys get yours yet? You guys got it? Are there going to be enough? Woohoo! All right. All right. So take a look at that. I'll start putting the database or the table on the board. Oops, forgot a column. OK. Is anybody confused? Yeah. All right, let me start you out. There. Started you. The first one that we're looking at, we're trying to go from vertex 1 to all the other ones. So we start with vertex 1. OK? It's 0 distance to vertex 1 from vertex 1, so we fill that in. What nodes does vertex 1 go to? 6, 7, and 2. So how far is it from 1 to 2? 20. How far is it from 1 to 3? It's not, right? So we just leave it as infinity. Same thing with 4. Same thing with 5. How about 6? 10. And then 7? How much is it? 25. OK, now we're not quite done yet. What we've done is we now know that 1 is known. We have done it. At no time are we going to get less than 0 for 1. So what we do is we say 1 is now known. What I normally do is I normally go like, you want to close the door if you can't see around it? What I normally do is I normally fill in this one all the way across because they're not going to be any different. Right? What's the one thing I forgot to do? Alice? Previous, yeah. So the previous to the ones I just changed was 1. So I need to make that a 1, and this one a 1, and this one a 1. OK. Because I'm a moron. That's why I crossed out 25. OK, hold on. 25. That one there. OK. I don't know why I did that. I'll let you see it. Yeah, I guess it's a long day. All right. Oh, sorry. Is that a little better? Maybe not. OK. OK, so we're done with 1. What's the next one what's the algorithm say that the next one we look at is? Why is it 6? OK, it's the shortest distance of the unknown vertices. So of the unknowns, the only one that's known right now is 1. So all the others, what's the least one? 6. So what I do is I write the 6 here, and I say, OK, I'm going to go now from 6. What does 6 connect to? 3, 4, 5. So is 2 going to change? No, leave it at 20. It doesn't change. Is 3 going to change? Yeah, what's 3? What's the distance from 6 to 3? 20, but we started 10 away from 1. So how much do we add those together? So what do we put here? 3, 30. Right? And then 4 is going to go from infinity to, let's see, 25 plus 10, so 35. Yeah? And then 5 is going to be 30 plus 10, or 40. And then 7, we can't get there from 6, so this is just going to be 25. And we're done. The what? This is 6. Oh, sorry, yes, 6. Yes, thank you. And what else did I forget to do? Previous. So which ones did we change? 3, 4, 5. They all came from 6. So 3, 4, 5. Nope, I'm still a moron. 6, 6, 6. How does that sound? 6, 6, 6. There you go. It's like one of the songs. OK. All right. So now, we're not quite done. We now finished 6. So we mark it as complete, true. And I normally just fill these over because I know they're not going to change. Okay. Get the idea? All right.
Same thing with 20. Fill it across.
20 has not been known yet.
Well, no, like the VC one. OK, do it. That's right.
We don't know it yet. Which one are we going to go to next? Of the ones that are unknown, 2, 3, 4, 5, and 7. What's the least? 2. So v equals 2, etc. OK? So keep going. I'll keep filling this out. I don't need to talk anymore, but unless somebody wants me to go through one more round. But I'll just start filling it out what I think. I'll probably make mistakes. So you have to keep me honest. All right? Let's see. 4, 2 goes 2. 7 and 3. 3, 15. Can't go up.
Wait. So. Is it 23 because you're doing the path from 1 to 7?
Did I do it wrong? No. No, we're doing a pass from 2. From 2. Okay, 2 goes to 7.
Oh.
And how much does it take to get from 2 to 7?
Oh, I see.
Takes 3, right? And 2 starts at 20. So 20 plus 3 gives you 23. Yeah, Danielle. Yeah, you don't want to make it. We're trying to find the shortest path, not the longest path. Yeah, so we just leave it at whatever. Yep. Because it's already 30, and we're trying to find the shortest path, so why would you write a bigger number if you can already get there by a shorter path of 30? Right? Yeah. Good. Yeah, that's good. Yeah, so 7. What do I have which?
23 for V7.
OK, so V7 was 25. And I was working on V2. So can 2 get to 7?
Yes.
And how much does it cost to get from 2 to 7?
3.
OK, so it started at 20 from at 2. 20 plus 3 is 23. Right? And notice I also changed it to come from 2 now. The previous is 2. Good. All right, lost my place. Let's see. 7 goes to 3 plus 2.
Can't you get 3 with 27?
You can get it to 25. 4, so I'm not good at 4. And 5. Which 25?
The V3 one across under 7.
Here?
Yeah.
OK, so we're looking on 7, and 7 takes how far? How much does 7 take to get to 3? 2. So it starts at 23. 23 plus 2 is 25. Because remember, we don't care about what it was. We care about the current path through 7. Sorry about the low board, guys. Okay. OK, let's see. So I've done that. OK. 4, 25 plus 3 is 28. Three goes to, that's it. Yeah.
Why is your, I get 32 earlier.
OK.
Like in the V5, V3 column, I get 32.
In the V5, V3 column, you get 32. Somebody's going to kill me for doing this. OK. Say again?
I was thinking that like, so does it have like, to get 32, you go like 1 to 2 and 7.
Get 32. Hold on. Don't worry about where you're going from. Just go from what you're at. So 20, you're working on vertex 4. How far is it from 4 to 5?
Well, no, I know how that one works, but like the one before it,
Which one before it?
from 3 to 5.
OK. 3 to 5 doesn't change.
Why? Is this because there's no path?
There's no path.
Oh.
Yeah.
Yeah.
Make sense?
Yeah. I just like, I want the path from 3 to 4 to 5 to count.
Yeah, you will get it. It'll get there. It'll get there.
So it happens
Yeah. Okay. Whew. All right. Do we think we have a kind of a handle on this? If you want to practice another one, there's one in the back that you can do for V4. It's a little weird that you can't get to some from there, so you'll end up with infinities. But I've put the answers online. If you want to look at the answers, it's on the lecture slides for today. Anybody have any questions about this one so far? One thing I want to do, how do we get to vertex 5 from 1? There's a real easy way to do it. Yeah, go ahead, Erica.
You find the previous of 5.
OK, so what's the previous of 5? 4, because the previous of 5 is 4. This is 6 is crossed out. OK, 4, I'll do it downwards. Then what do you do? What's the previous of 4? Previous of 4 is 3. What's the previous of 3? 7. What's the previous of 7? 2. What's the previous of 2? 1. Is that how you get from 1 to 5? 5. So you go 1 to 2 to 7 to 3 to 4 to 5. And that happens to be the shortest path, right? 1 to 2 to 7 to 3 to 4 to 5. You wouldn't necessarily think that was the shortest path by looking at this straight off the bat, right? But the algorithm finds it. OK? Yeah. So you should be able to do this. I'll have something very similar to this on the final. Very similar to this. OK? I kind of like having Node monitor here now. Opens everything up. All right. Anybody need any last minutes on that? I'll leave it there. OK. You want to take a 2-minute break now? Let's do it. Take a break. Do we what? We don't. If you know what? I'm still looking for stuff to cover in like the last week of class. So if you want, maybe we can do that. Wednesday, I'm going to do some kind of esoteric ones. No esoteric data structures. Like we're gonna talk about a rope, which is an interesting one. We're going to talk about what was the other one that I was looking at? Skip lists. I think I had that at the end, but I'm going to do it this week. And then there's one other one that I wanted to look at. Skip lists, rope, another random one. I forget what it is. It's on the webpage. That's it, Bloom filter. Yeah, those are pretty cool, actually. No. We had a handout a couple weeks ago. The what? Packet. We had the packet. That was a while ago. Then we had something else, too. Forget what it was. I didn't hand that out. I don't know. I don't know. How'd that come out? All right? Kind of getting it? Yeah. A little more practice, you'll get it? Perfect.
Yeah.
Good.
So is like, are you going from this view to this view? Or this view to this view? So how should you think about it?
So this is the node you're at.
Right.
So you're saying, where does 5 go to?
So 5 to 1, infinity, because you can't get
infinity.
Same all the way through. 5 to 4.
5 doesn't go to anything. So all this column is going to stay exactly the same.
OK, so you're putting the lowest path that.
Yeah, so far. Well, the one in the previous one.
Right.
If it's not
even though 5 can't go to 4, it's still 0 because you're starting.
Right, still 0 because you've already gotten to 4 from 4.
That's good. 10, never going to 7.
Say again?
Because like once you go to 3,
yeah.
then it goes
7 to 1.
Yeah, but it doesn't matter because you ignore 4.
Right, 5 doesn't go to
Well, right, but you still have to look at the other. Yeah. 16? Oh, you go to the right. Is that the least one? Yeah. Yeah. Like I said, I put the answers online. So.
12 there, right?
Yeah, but this is 10.
Yeah.
Yeah.
Do you
They're on the lecture website. Oh, there they are.
The total path.
Oh no, that's not it. Look at
I'm just
the
looking at it
lectures.
to
What's
see if
that?
I
Oh,
can figure
oh,
it
okay, cool. What's that?
So the total path length from 4 to 3 is 12, but so you put 12 there, right?
Yeah, but right, but you don't.
2 from 7 to 3.
Well, remember, are you working on 7 yet?
Yeah.
You're working on 7. So what is 7 now?
What do you mean?
How much is 7 in this column?
Infinity?
It shouldn't be.
Oh.
You
this
can't.
col-
Then you shouldn't be working on 7
this
now.
column, it's 10.
Okay, so
Yeah.
10. So how much more is it to get
No,
to
it's
4?
2 more.
Or to get to
3. So
3?
it's 2 more, so it's 12 total.
Okay, so you see how you do it? You don't even
Yeah.
worry about, oh, it's going. You just look at the last
I
column.
get the idea. I just like writing it down. It's from 7 to 3 is just 2. But these boxes are getting the total.
Total, yeah.
Okay. I think I know how to do this.
Okay,
So
good.
7, 6, and 13.
Yeah, what's up?
So I like got to 6, right? But then it goes back to the ones we've already done.
And that's okay.
Then you just stop here,
Well, I would still do 1.
even though it's infinity.
Sure.
So you would,
What's infinity plus infinity? Is that going to change anything?
no.
No. Just put infinity in those ones. You're done.
And then they're technically true, even though,
Yeah, they've been solved.
right?
They don't have a path there, but they've been solved.
And then they just don't have a proof.
Great. Yeah. Good. Hi, Graham. You have some infinities. Yeah, 1 and 2. I think rows 1 and 2 will both have infinities. Yep. Good. All right. So let's get back into a little more analysis here. Okay? So this Dijkstra thing works. We know it works, and we've kind of shown that it works. I suppose we haven't proved that it works, but we've shown that it works anyway, with lots of examples. The question is, how does it perform? Right? What do we have to do at each stage? You were making a decision. What was that decision? What was the decision on how to pick which vertex we were going to next? It's the one of the other vertices that's what? The least, right? Of the ones that are not solved. So you could have to go through, except for the ones that are solved, all of the other ones. So that's at least going to be on the order of the vertices. Then you have to walk through each vertex and see where it attaches to, which could also be on the order of like the number of edges, right? So you're in, and kind of really it's just the number of vertices. You could have to go to all the other vertices, right? So what kind of performance are we talking about? The number, by the way, the 2 lines on either side of V mean the number of vertices. So we're basically on the order of the number of vertices. Whenever you see that V squared, the squared in there, you know you're going to be like, oh, that's not good, right? And I will tell you, lots and lots and lots of lots and lots and lots of problems use Dijkstra's algorithm. So we want to see if we can do better than V squared. Okay? Instead of scanning down all of them, maybe we can do a little better. Okay? If this took me forever to write, to figure out. I tried copy and pasting, but it took. I remember it took forever. But anyway, most graphs are not this way. But if you have a graph that's like what we call dense, which means like lots and lots of different edges, you're not going to do better than that. There's really no way to do better than searching through every vertex every time, because everybody's connected to everything. You just have to check. There's just no way really around it, right? So that's the worst you're going to do in that case. But most graphs don't look like this, right? They look like this, where there's a few edges. We call this a sparse graph. Okay? It's a sparse graph because there really aren't that many edges. Notice 7 has 2 going out and 1 coming in, instead of 6 going out and 6 coming in, right? There's many fewer edges than there could be. When you're dealing with sparse matrices like this, or sparse graphs like this, okay, you end up, we can hopefully do a little bit better. What do you think? Here's your hint. We are trying to find the minimum value of the unsolved vertices. What kind of data structure might we use to find the minimum value? Think about that. Tell your neighbor if you've got one. What do you think? Yeah, Owen says you could use a heap. Yes, right? A heap is the perfect data structure to get a minimum. That's the whole point of it, right? That was we spent all that time talking about it, right? A priority queue, which we build out of a heap, right, is every time, what we're going to do is every time we change a distance, we throw that into the heap, and then we take out the minimum. And that whole process is logarithmic because it's a heap, right? Awesome. So that's what we do. I'm going to show this to you, OK? I'm going to show you how this actually works. Here's your heap. Just like with all these kind of algorithms, you have to start somewhere. We're going to put an element into the heap and then immediately take it out again. It just works out with a while loop the way it works. But there's your heap. OK, it's vertex 1 with a distance of 0. That's what I put up in the little corner here. Distance of 0. You take that out. OK, you do delete min, and it gives you that one. You take delete min, and you say, OK, fine. You mark it as known. If you take it out of the heap, it is now known. You're done with it. Well, I mean, you're done with it in terms of the rest of the algorithm. But what you do is then you say, what does this one point to? And it's the same exact thing. Vertex 1, in this case, points to 4 and 2. So we've got to put those in the heap. OK, vertex 2 is going to go in with a 2. Vertex 1 is going to go in with a 1. Does it matter what order we put them in the heap? No, because we've got an insert that bubbles things up, right? So it's going to work out fine. If you put the 2 in first, then you put the 4 in, the 4 will pop up to the top, right? So it doesn't actually matter. So then now you've got this heap. I know it's still kind of a wimpy looking heap, but it's a heap, right? It's got a 1 and a 2, and it's a min heap. OK, so then you get the min. And you get the min, and you say, oh, OK, if I get the min, so the min is now 4. And we go, fine. 4 is now known. We're going to mark it known. And then we're going to say, OK, what does 4 point to? Well, 4 happens to have lots of adjacent vertices, right? It's got 7 and 6 and 3 and 5. So we update all those and put them all in the heap. Now the heap's becoming more heap-like because it's nice and big. OK. Notice something. There are duplicates in here of the keys. It doesn't matter. They'll pop out in whatever order, and it won't matter. Remember, you could pick either order in Dijkstra's algorithm for ties. Still works. OK. So then we take v2 out, and we marked it as known. And then we adjust. We look at 5, because v2 is now goes to 5 and 4. 5 actually doesn't change because it's already low enough. So you don't do it. You don't put it back in again. OK. And then you get 3 out. You get 3 when you do 3 out. OK. And now you adjust v6. And v6 does need to change. It actually goes down to 8 from, I believe, 9. It goes 9. Yeah, it goes from 9 to 8. And then you put 6 on there. Notice something new now. There's actually 2 v6s in the heap. Well, who cares? If you remove min and you already know it to be true, ignore it, and then do another remove min. It works fine. OK. All right, and then delete min returns 5, and you have to look at 7, but you don't change anything, so you don't put that one on there. Then delete min removes 7, and we do have to change v6 again. And now we've got 3 v6s in the heap, which seems ridiculous, but it doesn't really matter. We're going to dequeue one. We're going to deal with it, but we're almost done. We dequeue the v6, and then we're done. And now we've got we know this to be true. So when we do the delete min for these two, we just ignore them, and we're done. And the heap is done, and we have solved it. OK? Much better running time. Much better running time. In this case, yeah, Dave.
So is there a way to leverage this, though? Like, for example, if you're using Google Maps or something, and then you get like the first few results for the quickest path, you get like, I don't know, this instruction work on the quickest path. Is there a way to leverage it to not just give the best result, but give like the top view, so that one doesn't work for some reason? That's pretty good. Thank you.
That is a good question about like how do you find like the next best path?
Right, because it seems like if you say, OK, we have 2 there, 3, so we're going to take one of them at random and ignore the other one.
Yep.
You're kind of missing out on like, well, that option might not work, but this other option is just as good, but we missed it.
Sure. Yeah, I think what you're doing in that case is when you're trying to find like what's the next best, you're doing like a variation of Dijkstra's algorithm. But then what you might do is you might say, I'm going to redo Dijkstra's algorithm, but cut out one node as if I can't even get there, or something like that. And then it'll redo it and say, oh, now this is now, the, according to this, without this node, it's cheaper.
Yeah. Find a way to like keep storing the data
Yeah.
in a way that would be efficient enough that you wouldn't have to keep running.
Sure. I mean, Google obviously does that because they give you choices, right? They can say you can go this way and it's 30 minutes, and this way it's 32 minutes, and this way it's 35 minutes, and they give you a choice, right? So you can do that. Yeah.
I guess there's also like a detour button you can hit.
Oh yeah.
As you're driving, so you can hit the detour button, it'll like pop you off to the next.
Sure. Sure. Yeah, you can. Right. You can. There's lots of ways you could augment this to be for your particular situation. Like if there's an accident or something. Oh, I need a detour or whatever. Yeah. So, but remember, we're kind of talking about the lowest like denominator here in terms of figuring this part out. But how you add to it, I guess if we had another semester, that would be project 7. Yeah.
So is there like a distinct line for where a graph is no longer sparse and you consider it dense? Like how do you,
Yeah.
do you just eyeball it?
I don't think there's a distinct line. There may be some formal definition of whether something's dense or sparse, but for the most part, you eyeball it. I mean, let's put it this way. This will also work for the dense ones. It's just not going to do any better than the other one if it's dense. So you would want to use this one no matter what. But yeah, if you had to decide, is this dense or not, you might be able to say, okay, if there's more than, the square root of the vertices number of edges, or I mean, there's probably some heuristics you can use.
But you wouldn't really have to figure it out because you should just use it.
Yeah, you would want to use this one in this case. So as it turns out, right, what you're doing is you have to look through each edge. I mean, you still do have to look at each edge, right? But for each edge, you do a delete min, and that's a logarithmic based on the number of total vertices, right? So what we actually have is on the order of the number of edges times the log of the number of vertices. Okay, I'm not going to make you memorize that, but you should just know that you can get logarithmic behavior out of this sort of algorithm. Okay, which is kind of neat. All right, next. Uh-oh. We already talked about this a little bit recently. If you have negative edges in here, Dijkstra's algorithm in its normal form is going to fail. Okay, it's going to fail because it's greedy. And it says, right now, I know what the best is, and I can never get better. In other words, you can never get smaller distances, right, or smaller weights as you go along. There's no way to get a shorter path than the one you're already at, unless you have a negative edge. And if you have a negative edge, now you're in trouble because you could be doing something over here. I was trying to think of an example in this graph which works. But let's say you're going to 6, right? If you go to 6, you could go 3 to 1. Let's actually do this. 3 to 4 to 6, right? That takes 10. And you're not going to get any better on this half. But what if you went this way? 3 to 1 to 2 to 5 to 6 to 4 to 6, guess what? Or to 7 to 4 to 6, guess what? That negative 40 will make it so this is actually less. So our greedy algorithm fails. Okay? How might we solve this? Can you think of an idea of how we get rid of that negative weight in there? What do you think, Danielle? Oh, if we increase all the values, what do you want to add to them all? 40? Let's add 41, so at least it's 1, right? OK. So this will become 41, and this will become 49, and this will become 42, etc. OK, I like that. Is there going to be an issue with that? That's exactly what Danielle's saying. I called it naive, but that's not meaning you're naive. That's like the one that you might think of. All right. So here's what we have. All right. If we have this, what's the issue now? Take a look at a couple paths and see if you can figure out what's going on that might cause us a little bit of trouble. Dijkstra would work in this case, but what do you think, John?
Well, it still kind of favors that V7 to V4 because it's still offset. You're not losing value, but it's just comparatively so much less.
OK. It definitely favors this one, but that kind of makes sense because it still was way less than the others. So you're right there. I'm just thinking there's one other issue here that could become really bad. Yeah?
Now it's penalized based on the number of things you go instead of just distance.
Yeah, it's penalized by the number of every time you jump another one, you add 40 more, right? And then it's not like at the end you can just subtract 40 and be done with it. right? You've got an issue where you're now, if you're going from here to here, you've got 40 more and then another 40 more. And if you had another, you go another 40 more. So you see how you get penalized by the distance you're going, right? The paths with many edges become more weighty than the ones with fewer edges. So all of a sudden you're in trouble in that case. Somebody came up with an interesting idea early in the earlier class. Can anyone think of one way to like mitigate that in the end? What do you think? Go ahead, Allison, then I'll let you go. Go ahead. If you kept track of it, I'm not sure that would still allow you to solve it properly. Like I haven't worked it out, but that might be an issue in terms of you still might not be getting the right answer with the greedy algorithm. That might, because in the end you're kind of doing the same thing in the end, but just not in a different order like than you did before. So this isn't going to work. All right, this is not going to work. You're penalizing yourself too much on this. So what do you do? Well, what we can do is we can kind of combine the weighted algorithm and the unweighted, Dijkstra's algorithm, in a way that we basically say, all right, all of this known column here, I can't really use that anymore. You have to basically go back and re-look at all the other nodes again, because you can't do the known one. You can't make it known when you think you could, when you could before, because you might run into this case where you get into a case where it's less. So what does that mean? Well, what we can do is we can use a queue. Of course we can use a queue. All right? We use a queue now, regular queue. What you're going to do is you're going to dequeue a vertex and then find all the vertices that are adjacent such that they would go up in value, or rather, they would go down. Put those back in the queue and keep repeating until the queue is empty. So instead of saying now it's known when you get done with a vertex, you could have another. You could have one that you've seen before go back in the queue, and you have to deal with it again. Okay? I will show you what I mean with this in a little example. Okay? Watch the example. Same ones we've done before, except now we've got a queue here that we're putting in here. Okay? Whether or not it's in the queue, these stand for infinity. I don't know why I didn't use the infinity symbol. Those are infinities, and the previous is there. Okay? So we put v1 in, we dequeue it, okay, and we check the weights for v2 and 4 and update them. Okay, and 2 and 4 have got to go from infinity to 2 and 1. Okay? So from infinity to 2 and 1, and we put both of those in the queue. We just changed them. They have to go in the queue. Okay? Change them, they have to go in the queue. So dequeue 4, because this is a first in, first out, right? Dequeue 4 and check the weight for v6. Okay? Did I do that for? Did I dequeue 2? Oh yeah, I missed this one. Dequeue v2 and check the weights for v4 and 5, right? And update and place them in the queue. Oh, what am I doing? Sorry, I'm going backwards here. There we go. There we go, and then there we go. OK. And then you do the same thing again. I'm going to run through this a little quickly just because we've seen this a million times. But dequeue 5 and check 4 and 7. If anything changes, you place in the queue. In this case, it doesn't. Right? Dequeue v6, no weights to check. Okay? And you go, ooh, I'm getting there. Dequeue 7, and now you're in trouble. Not in trouble, but look at this. 4 is going to have to go back in the queue, because it was getting lower, 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 right, to 1. Or it was nice and low at 1. But now it's going to be negative. What is it going to be? 7, which is 18. 18 minus 40. What is that? Negative 22. There you go, negative 22. But 4 needs to go back in the queue, because now the fact that you've changed this one means that some of the other ones that it affects, like 6 maybe, actually that's the only one, 6, has to get changed as well, because it's now you've gone down that path, right? And then you do change 6, and then you now 6 is negative 14, and then you dequeue 6, and 6 doesn't go to anybody, so we're done. Okay, so this works. Woohoo! Right, it actually works. It's kind of slow though, right? This one is actually on the order of the number of edges times the number of vertices, which is basically the number of vertices squared in this case, right? If they're more or less the same number going in and out, and it's significantly worse. But the trade-off is because you have you have to deal with this negative edges. Yeah.
Would this only work if there's a vertice that doesn't have an outgoing path?
Very good question. In other words, would it work with 6
6 foot length anyway?
Well, yeah, if 6 went somewhere, you could end up with a cycle, negative cost cycle. Then you're in trouble. That's actually the next thing here, right? If you have a negative cost cycle, let's say I change it so this goes this way, right? If you do have a negative cost cycle, you have to stop sometime. Okay, and what you do is you stop after every vertex has been dequeued vertex plus 1 times. Now, what I think is a little strange about this comment is that you may never get back to some of these ones. So you can't dequeue this one that many times. So you just got to make I think that statement's a little misleading. But the point is, you can just decide, look, I'm going to stop at some point. It will be a shortest path at this particular time. But because there's a cycle, you could keep getting shorter and shorter and shorter, and that is ridiculous. So that's that. OK? Any questions on this stuff? As I said, graphs and things are, it's a huge, huge topic, right? Huge, huge topic. In fact, in the wild, we see this all the time. We see the use of Dijkstra's algorithm all the time. We've already talked about Google Maps, right? Shipping costs, right? If you are a shipping company, you hope that the people you hire to do your routing know something about these algorithms, because you don't want them routing you through places that are going to cost you more money in time or gas or whatever. So you have to think about that sort of thing. UPS has very interesting routing. FedEx and UPS have very interesting routing algorithms. A number of years ago, I saw this post online about how UPS they try to only make right turns with their trucks, right? Because why make left turns across traffic when you have to wait for traffic if you can keep making right turns? So they have these algorithms that are routing algorithms, and they go, look, we're gonna say a penalty. We're gonna give you a huge penalty if you go left in terms of the algorithm, right? So they change all the weights of their algorithms to say it's not 1 mile, it's like 5 miles if you take a left, right? Because they want to figure out the algorithm, and then they push the button, and then it goes, OK, your truck's gonna go bing, 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 all around the city, and it's actually gonna save you time. Clever, huh? Really pretty darn clever. And some computer scientist gets no glory for that. Well, he did get glory in a Wired article or something, but that's kind of cool. So whoever thought of that is pretty smart, right? But shipping's a huge one. Computer networks, of course, computer networks use these sorts of algorithms because they're literally graphs. Well, figuratively, I suppose, but they're graphs in the computer science sense that they're all linked together, right? OK, they're all linked together from one computer to the next. You guys know about peer-to-peer computing, where you're talking about BitTorrent and all that. If you think that your computer by itself is connecting to somebody else's computer without going through other computers, you're crazy, right? There are lots of other computers in the way. There's just no one central server which is handling it all, right? You still have to go through all sorts of computers, okay? That's why the NSA loves that sort of thing. Telephone networking. So the best path for a call. Did anybody ever call Europe or Australia or something like that? Ever have any friends over there, like some other countries? And you ever get on the phone and it's like a huge delay, like when you're talking, and it's kind of annoying. Yeah, if you're talking to someone in somewhere else in the world. Anyone know what causes that delay? What causes that delay? What do you think? Physical distance, kind of. When I call England, though, right? I have a friend in England, and I call her up, and I say, hey, how's it going? And it's a delay. And I'm like, this is really annoying that it's a delay of about 1/4 of a second. You can hear that, and it's kind of painful, right? Not painful, but it's just annoying. The delay, there are wires underneath the Atlantic Ocean that go from here to England, right? And 3,000 miles is not that far to go. It's not that. It's when I get on the connection that doesn't go through the ground, it goes where? Into outer space, right? Which is kind of cool to think about, that my voice is in outer space, right? But it's what it's doing is there's satellites that are communication satellites in what we call geosynchronous orbit that are going around the Earth. Anyone know how far away geosynchronous orbit is? First of all, how far away is the space station? How many? Sorry? 20. That would be pretty close. It's about 200 miles, actually. Yeah, the space station's about, the International Space Station is about 200 miles away. Space shuttles, when they were going, 200 miles away. But the satellites for the geosynchronous satellites, how far away are those? How about 23,000 miles away, right? They're a long way away. It's at 23,000. It might be more like 30,000. But whatever, it takes about an 1/8 of a second for light to get to that satellite, and another 1/8 of a second for light to get back, which means it takes about 1/4 of a second when you're talking to someone in England, if you're bouncing off a satellite, for them to hear you by the physics of the universe, right? Nothing you can do about that, which is why it's kind of annoying. Which is why you hang up and you call again and hope you get a landline, because it's much faster. Yeah.
Why do we use those if we have fiber?
Why do we use those if we have fiber? Well, it depends, because it depends on the bandwidth. It depends on who's calling, and I mean, if it's like Christmas, you're going to call, like lots of people are calling, they might need to use it, you know. But it might also be cheaper depending on whoever's the phone call is routing through. Yeah. So it depends. But anyway, telephone networking, definitely used for Dijkstra's algorithm. And of course, subway systems. Anybody ever been to Tokyo? I've never been to Tokyo. The subway system there is gigantic. I mean, it looks like it's huge, but our little T is kind of small compared to some of these other giant subway systems. And then, of course, you can also do map searching with Dijkstra's algorithm or some other algorithms. In fact, we will do more algorithms in the graphing, not Dijkstra's, but we'll do other graphing algorithms similar to the search ones we did for the maze that we did a couple months ago. All right. Anybody have any last-minute questions on graphing, the project, etc.? OK, I'll see you guys Wednesday.